Hi, my name is Emma King, and this is my Lab 5, and I chose to do the human rocket. So a little bit of background information. This is about a man named Felix who attempted to be the first human to break the speed of sound himself, which he did by jumping out of a ship thing from over 36,000 meters from Earth. And for this lab, we utilized Newton's second law and the momentum principle to model his position and velocity as he skydives from the ship to Earth, and understanding the concepts of density and air drag and air slash drag resistance. We could model the forces acting on him as he travels through Earth's atmosphere. So the main equations that we use for this is F net equals F drag plus F grav, and then just our basic velocity update equation and position update equations. So Vf equals Vi plus F net over mdt over m times dt, and then final position equals initial position plus the velocity times delta t. And so the main thing we had to consider in this is the fact that the drag force is going to change depending on the pressure, density, and temperature of the atmosphere for each level of the atmosphere. So this is also just a little picture of what's actually happening. So the drag force is pushing him up basically, and gravity's pulling him down towards Earth. So this is where I got the information about how the atmosphere is working. So it's like a NASA model. And so for what this is when he's in the upper stratosphere, this is what our temperature and pressure are going to be, is based off these equations, with h being his current position from Earth, so current distance from Earth. And then for the lower stratosphere, which is when he's between 11,000 and 25,000 meters from Earth, this is the equations. And then when he's in the troposphere, which is what we're in, that's the equations for it. So the main thing we have to think about is the fact that less dense air, because it's not as dense, it's it's easier for stuff to fall through it. So there's not as much drag force pulling him up. So that causes him to move faster, because then there's nothing resisting that the force of gravity pulling him down. So this is my code. So this is the initial data. So this is his mass, which I found from just I just Googled the mass of a man, average mass of a male, and it was 86 kilograms or whatever. And then his position, that was his initial position, which was at 36,576 meters from Earth, and his initial velocity was obviously 0. And then his time and his I just did a dt of 1, and then gravity and the unit vector, because we just really want to consider the y component of this. So here's my code. So the forces, all of these three sets of equations came from this picture right here. So this is just these three exact equations plugged in. And then down here, that gave us the density, which is this equation that's here. All of this was given to me out of that graphic. And then, so then we have the weight force, which is just his mass times gravity. And then it's negative, obviously, because it's pulling down on him. And then the drag force is going to go up, so it's positive. And the equation for the drag force was 1/2 times the density times 0.557 times his velocity squared times j hat. And that 0.557 is just a constant for the equation of the drag force through the Earth's atmosphere. And then I just added these forces together to give me F net equals FD plus the weight force, which was obviously give you the total force pulling down on him. And then I put in Newton's second law, we've done in every lab. So we have his velocity equals his initial velocity plus F net over m dt, and then final position equals initial position plus his velocity times dt. And then I just updated position and everything. So this is what my graphs ended up looking like. So we have the velocity versus time graph on the left, and then the position versus time on the right. And as you can see, at the beginning, he's moving the fastest, and his acceleration is really high, so he's moving very quickly. And that is because that's the least dense air, so he can move the fastest through it. And then as he gets closer and closer to Earth, it starts to taper down, because he can't move as fast through the Earth's at like the troposphere. And this is his position, so he starts up really high up there, and then he just goes all the way down to Earth, and they take the same amount of time. And obviously, you can see it's not a linear because like the position, I mean, the velocity is changing as he's going. And my discrepancies are most likely due to the fact that he he was actually probably weighing more than the suit, like more than the average male in that moment, just because the suit weighed a lot. Because like he really moved about like 380 meters per second, and we can't say that this perfectly modeled the behavior that day.